the University of Strasbourg. From 2018 to 2021, he worked at the Stockholm University in Sweden. Sir has published over 30 research publications in reputed, peer-reviewed international journals and delivered more than 20 invited talks at scientific conferences, workshops, and seminars. Today, Sir will be talking about how do galaxies like the Milky Way form in our universe for the webinar. Now, I may request Dr. Kathy Malhan to share his valuable knowledge in his area of research with us.
Yes. Hello, everyone. Can you see my screen and also hear me well?
Yes, Kathy.
Perfect.
Yes.
Thank you, Ria and Vashista, if I'm not mistaken. Thank you so much for the generous introduction, and thank you so much for Amit sir and all the organizers for having me here. It's a pleasure. I truly wish that I was there with you in person, but it's still a nice way to be linked with all of you and talk about science with you. So today, I will be talking about the topic, namely, how do galaxies like our own Milky Way that we inhabit form in our universe? And it so happens that it happens to be one of the high priority questions and one of the modern mysteries of the field of astronomy, that how do galaxies form? As you'll see as I proceed with the presentation, the path that I've chosen is not to confuse you or perhaps bore you with the nitty-gritty and the details of this topic, of the subfield of astronomy. But rather to basically, my agenda today here is to kind of excite you about this new field, because I know that many people they know well of the field about black holes or radio astronomy or other classic, well-detailed topics of astronomy. But I think the questions such as how do galaxies form, how do stars form, for instance, are kind of new, that are not well known to many students, is the impression that I have. That might be a wrong impression. So my point here really is to kind of excite you about this field of galaxies, is to motivate you about this field of galaxies that you may pursue if you go down this path of physics and research in physics. So now I'll start, and you may feel that I may be walking rather randomly as I proceed with the presentation, but that's only because to give you a taste of this field of galaxy rather than to try and teach you or make you learn something about it, rather to make you learn about getting excited about this field of galaxy. Right, so this image that I showed you initially is basically an artistic impression of the galaxy. And there are various components. So one of the fundamental things that we do is that we take an image of a galaxy and then we try to learn about its structure. And as you can already see in this figure, there's lots of structure. The galaxy is not a smooth system. Every point here is a star. And the stars have kind of structured in this galaxy in a rather messy way. So when we try to disentangle the system and we say that, okay, this is the position of the sun. So the sun is not at the center of the galaxy, for example, it's at some distance from the center. And this is where we make all the observations of the universe, because Earth is somewhere around. This is basically our solar system. And the mass of the sun is about 10 to the 30 kilograms. So it's a really massive star, the sun. Then we have the center of the galaxy, where sits a supermassive black hole whose mass is 10 to the 6 solar masses. So one thing that we astronomers do is that we try to quantify all the masses of the universe in terms of solar masses. So then the mass of the supermassive black hole would be 10 to the 6 times 10 to the 30 kilograms. But we quantify everything in terms of solar masses just to make our calculations less complicated. Then the structure that you're seeing here, all of this is the galactic disk, because the stars are distributed in the form of the disk, and its mass is 10 to the 9 solar masses. So quite large masses we are talking about here. So it's equivalent of saying that there sits about 10 to the 9 number of suns in the galactic disk. So it's a vast number. And then the remaining sky that you're seeing here, it's galactic halo that is less dense. There are more stars in the disk because, of course, it's brighter compared to into the halo. And then this galactic halo comprises of stars, a little bit of gas, and also dust talking a little bit of dark matter as well as I proceed. And then this brown stuff that you're seeing here is basically the dust. And by the dust, I mean these are literally dust particles that are made up of oxygen, atoms like carbon, silicon, magnesium, or other higher order compounds. So this is just to introduce you how a typical structure of a galaxy looks like, how our Milky Way galaxy looks like. If we were to go outside into the space and then take a picture of it, of course, this is not possible because all the pictures that we take is from the Earth. So actually what our galaxy looks like is this, because this picture is the real picture of our galaxy taken from the European Space Agency's Gaia satellite. So Gaia is a satellite that you can see here that's orbiting the Earth. And then this is the map of the heavens. This is the map of the sky that it has created. So basically that picture has been taken from here, from this reference point, because this is where we are sitting and this is where the satellite is. So when we map it, we are basically sitting inside the Milky Way, and this structure that you're seeing here, it's basically the disk that we were seeing here. It's just a perspective. And then all of this is halo that you're seeing here. And what Gaia is doing is that it's trying to map the positions of the stars, the distances of the stars, the speeds of the stars in our galaxy. So this is just a short view of it that you're seeing here. The Gaia satellite was launched in 2013 by European Space Agency. And then its task, as you can see here, is to scan the sky and scan the phase space information of the stars. And I'll be talking a bit about Gaia as well. But this is one of the reasons of highlighting Gaia was because it happens to be one of the most famous and one of the most exciting surveys of the galaxy that many people are today working on. Subfield of astronomy, that is galactic dynamics, structure and formation, and in short, it's sometimes also called galactic archaeology. So people like me who are working in this field were also sometimes referred to as galactic archaeologists, because like a typical archaeologist who's digging into the Earth, and as the deeper you go, you basically try to find that, okay, 65 million years ago, there were dinosaurs, and then 300 million years ago, there was some other species of animals and plants, and you're just trying to learn how the Earth formed or what happened on the Earth, what's the structure of the Earth. Galactic archaeologists basically dig, instead of digging into the Earth, we dig into the sky, we dig into the stars, and then we try to find how do galaxies form or how do the Milky Way form. So the part of the motivation is to introduce this flourishing field of astronomy. Then we'll move on to try to answer some fundamental questions about Milky Way, such as why do we study Milky Way? How did our galaxy form? What is the Milky Way's dark matter gravitational potential? So these are the kind of stuff I'll be introducing and talking about. Then towards the end of the presentation, I'll be talking about some of the ongoing and upcoming surveys of the Milky Way, of the sky, that what are these satellites doing and how are they gaining information of the stars in our galaxy and also in other galaxies. And then in the end, we'll conclude and we'll have discussions. So this is, again, an artistic impression of our Milky Way. This is really what it looks like. So it's the disk. You see some spiral structures. This is where the sun is sitting. This is the side view of the galaxy. And then this is the hypothesized top view of the galaxy. If you were to send some satellite at the top of the galaxy and then take a picture, this is what the galaxy would look like. So this is where the sun is. This is where the center of the galaxy is. You see some bar structure. It looks like a chocolate bar, and it's really a bar. We call it a galactic bar. And then there are lots of spiral arms that are coming out. These are basically distribution of stars. So our galaxy, as you can make an impression from this, it's not a smooth distribution of stars, or it's not as smooth as we generally see when we Google Milky Way or galaxy. It's really actually messy because it's a messy scenario of formation of stars and starbursts. So again, just trying to give you a taste of what a galaxy looks like or what are its components. To also familiarize you with some of the numbers. So we think that the galaxy formed about 12 billion years ago, right? So basically the age of the universe is 13.8 billion years, and the galaxy formed just about 1 to 2 billion years after the formation of the universe. So it's 12 billion years old. The diameter of the Milky Way is 100,000 light years or 30 kiloparsecs. So it's another unit. I know that generally we talk about in terms of light years, but light years is again a very big unit. So we try to compress it in terms of kiloparsec. So this disk that you're seeing here, or the disk, stellar disk, galactic disk that you're seeing here, is basically 30 kiloparsec wide. The rotation period of a star is about 250 million years. So this is basically to say that it takes about 250 million years for a star to complete its orbit around the galaxy. So that's the speed of a sun, the time that it will take it to go around the galaxy and then come back to the same position. It's 250 million years. The typical speed of a star in our galaxy is 200 kilometer per second. So that's 720,000 kilometer per hour, or 7.2 lakh kilometer per hour is the speed. It's a gigantic speed, as you can imagine. And then the total mass of the everything in terms of solar masses. So if you were to do in kilograms, because I imagine you must be used to SI units, so that would be 1.5 times 10 to the 12 times 10 to the 30 kilograms is the typical mass of the Milky Way galaxy. Just to give you an impression how big these numbers are, and that is what makes these really exciting, these extreme properties that the galaxies have. Of course, Milky Way is not the only galaxy in the universe. We have known for quite a few decades now that there are lots of other galaxies in the universe as well. And we also have clusters of galaxies. So this bullet cluster, for instance, is a very famous cluster in the field of dark matter. So the observation of this cluster of galaxies, so each point that you're seeing here, it's basically a galaxy. Galaxies. If I'm not mistaken, it was 1970s or 80s when the observation of the cluster provided the evidence of matter. Just this picture that you're seeing. I won't go into the details, but this is just to show you some pictures how galaxies like to basically excite you about these fields. Then these are basically two galaxies that are hitting into each other. They'll be done colliding in a few million years or so, and they'll then mix up the gravitational field. This is our neighboring galaxy, Andromeda. So that's our neighbor. That's about 750 kiloparsec. So that's the closest galaxy that we have. And it has properties more or less similar to the Milky Way. Then we have this another galaxy that is edge on. So it's a disk, but you're not seeing it face on, you're seeing it edge on. And then this must be another, these stream of stars seen here must be another small galaxy that made contact with the galaxy, got disrupted, collided, and then it basically completely got disrupted and then formed these stream of stars that you're seeing here. And then this is another galaxy, which is a galaxy, and it has some spiral structure coming out of it. So that this variety of masses and morphologies, structures, galaxies have now observed, and it's really exciting to learn about them. This is the Hubble Space Telescope that was sent by NASA to basically and try and learn how the galaxies form. So at this scale, this is the Hubble Ultra Field that means then every point that you're seeing is a galaxy, not a star. Every single point that you're seeing, it's actually a galaxy. So this was basically one of the revolutionary pictures of that has ever been produced in the field of astronomy that showed you that the universe is filled with galaxies. And then, of course, actual question that comes to the mind that, okay, how galaxies form in our universe? How do so many galaxies form in the universe? And CSA, which is Canadian Space Agency. So it is basically successor of Hubble Space Telescope that will go deeper into the space. That is to say, it will probe much earlier time in the universe when the universe was really young and show us the baby pictures of the galaxies, the pictures of the universe. So it will go even beyond this picture produced by the Hubble Space Telescope. Shift gears, and now we'll so these were basically what I have shown until now, the observations of the galaxy. So now what we want to learn is we want to study how can we use models, our theoretical predictions, our theoretical models, to see if can we reproduce this observation that we are seeing. Because if we are able to reproduce this observation through our models, then that would mean that our model is mimicking the reality, the nature that we have. So these were the observations. Now we'll move to the theory. So one of the theories that we have, to, which is the recipe of the universe, that how universe would have been created, is called 3 parts dark matter and 1 part visible matter. So what this theory is saying is that by matter I mean, of course, anything that has mass is matter. So what this theory assumes, because theory always hypothesizes something. This theory is assumed that okay, the expansion of the universe, but if dark matter and baryonic matter, which are actually the matter of the universe, from which galaxies and stars form, and baryonic is the visible component of matter, and dark matter is the invisible component of matter. So now we have this theory. What we can do is that now we can to produce ways that can simulate universe, right? We want to simulate it. We can't solve the problem by writing equations, because we have 100,000 millions of particles, each particle representing a star, for example, each particle representing a galaxy. So we have 100,000 million billions, and we can't solve on paper, so we have to take help of a computer program, and then basically give all the cosmic mass of the dark matter, how much dark matter there is in the universe, mass of the visible matter, how much mass, the gravitational field, is it going as 1 by r squared, is it going 1 by r cube? That's your choice, because model you can give whatever you want. But the ultimate idea is to compare the prediction that will come out of this your program with the observations, because observation is the reality, and your theory is only a mathematical story unless and until you use observations. And that's when you point that you're seeing here is a dark matter particle, or you can also dub it as a star. And these nodes that you're seeing here, each single node is basically a Milky Way-like galaxy. So this Milky Way-like galaxy, this is another Milky Way-like galaxy. It's a movie, it's a simulation, it's not observation at all. It's from up there. This is one galaxy, this is another galaxy. As these galaxies infinity form, they're formed by the merging and accretion of smaller galaxies. This big galaxy in which smaller size galaxies are more play with, and they're getting disrupted, and the foreign stars that were in these smaller galaxies are then becoming part of this host galaxy, this parent galaxy that you're seeing here. So this is one of the Milky Way-like galaxy, this entire galaxy that you're seeing. Then these smaller galaxies are coming into it and then falling and disrupting, and then this is how the messy. This is really how the formation of the galaxy, how messy it is. So, for example, so the one of the first questions from these theory-based simulations, one of the first questions that we answer is that, okay, so our question was, how did galaxies like the Milky Way initially form in the universe? And then the answer that we get from these theories is that through merging and accretion of smaller galaxies. So this I'm basically showing you a similar movie, but a much simpler cartoon, is that if this entire galaxy was the Milky Way, then these smaller galaxies, so are falling into the Milky Way, and then the stars are getting disrupted, and they're forming this vast galaxy that the Milky Way today is. Right. This we have also seen not only in theory, but also in observations. So the left 3 panels that you're seeing here, this is observations in one of the galaxies that we have observed, second galaxy we have observed, third galaxy we have observed. So all 3 are observations of different galaxies. And on the right, we have computer simulations. And as you can see, that these computer simulations are basically telling us that, okay, Milky Way-like galaxies form through accretion of smaller galaxies. And then the observations are also kind of, the simulations are kind of able to reproduce the observations that you're seeing here, even though qualitatively, but they're able to reproduce. And then we say that, okay, it makes sense that the galaxies that we're observing in our universe must have formed through similar series of merging and accretion and falling of smaller galaxies into these galaxies. And the CDM model, this cold dark matter model, also tells us that galaxies actually sit in the halos of dark matter. So what we observe through our telescopes are basically just baryonic matter. What we really observe through our eyes or through telescopes or through satellites are either stars or gas. That's the only thing we observe. But theory tells us that in addition to stars and gases, there's also dark matter that we cannot see because it's not in the property of the dark matter to be visible. So it remains invisible. Of course, we can see it in simulations because we are running simulations. So we are the god of the simulation. So we can see everything in simulation. But in real life, we cannot see it. So when we observe a galaxy, we only see this. But theory tells us that there's also a halo of dark matter where there are lots of dark matter particles that are surrounding these stars that sit at the galactic center and also in the disk. So these are the kind of theoretical predictions that are coming out of theories, but we need to test them with the observations to basically test whether these theories are correct or not, because that's the only way we can test our theories. So that was the first question of how galaxies form. They form through merging and accretion of smaller galaxies. Then we have the second question. Do all galaxies have similar structure? This is another question that you can ask. Is it that all the Milky Way-like galaxies have similar structure, or is it that different galaxies have different structure? A different way of posing the same question is that in a given galaxy, how are stars and dark matter distributed in phase space? So it's basically the same structure, but it's a rather more perhaps physically correct question to ask, because by structure of a galaxy, what we really mean is how its components are distributed. So how the stars and dark matter and gas is distributed in phase space. And then we have learned through these simulations that no, it really depends on various factors. The structure of a galaxy depends on various factors, the local environment in which the galaxy is sitting. But one of the prime factors on what it depends is the nature of the dark matter particle, whether the dark matter is cold, warm, hot, or self-interacting. So by this, what I mean by cold, if we say that any particle in particle theory or in particle physics, when we say that any particle is cold, what we mean is that it is non-relativistic. Or to say, if it's moving, it has very low velocity. So it's cold. It's dynamically cold. It's not moving. It doesn't have a fast speed. It has a very slow speed. By warm, we mean it's still non-relativistic, but it's slightly moving faster. It has a higher speed. By hot, we mean relativistic speed. So at some sense, you can say that proton or neutrons are cold particles, and neutrinos are hot particles, because neutrinos has really large speed compared to protons or neutrons, for instance. And because we don't know what dark matter is, we don't know what its properties are. It's just a hypothetical particle that we have hypothesized. We don't know even if it exists or not. So we end up trying various different models of dark matter, whether it's cold, whether it's warm, whether it's hot, whether it's self-interacting. You can also build your own model suggesting can two dark matter particles interact, or they just cannot interact. So this is basically high-level particle physics theory. But when you do try these different dark matter models, you do get different structures of the same galaxy. So here I'm showing you again a computer simulation. Here I'm showing you the same Milky Way galaxy. So this is one Milky Way galaxy model. This is another model of Milky Way. This is another model of Milky Way. But the only parameter that has changed, and you can see that these different galaxies look very different, right? The only parameter that has changed is the property of dark matter. So in this case, in this galaxy, the dark matter is cold, meaning the mass of the dark matter is 10 to the 9 electron volts. So it's really heavy, really clumpy, and it's moving really slow in the universe. And you see that the galaxy that comes out of it, it's really structured. By structure, I mean there are lots of smaller galaxies, lots of structures that you can see. There's lots of structureness. When you reduce the mass of the dark matter particle, so now it's 10 to the 6 electron volts. That means now it's in the warm dark matter regime. The speed of the dark matter particle is slightly higher than the cold one. There's still structure, but the structure has reduced, right? So there were even smaller structures that were visible. Now all the smaller structures are mostly gone, and they're mostly higher mass structures, higher mass smaller galaxies that you can see distributed around the Milky Way. So the Milky Way, as I said, it's not a smooth distribution of stars. It's actually surrounded by smaller galaxies. Some of them were merged and accreted in the past, but some of them are today actually present that will be completely dissolved and disrupted in the future. So it's a messy scenario. And then if you further reduce the mass such that your dark matter actually becomes Bose-Einstein condensate, again, not going into the detail, but just to give you an idea, that it's your model, you can basically choose mass to be 10 to the minus 60 electron volt. It's up to you. So the structure of galaxy becomes rather smooth. We don't see any structure other than one or two structures that you can see, and it's more or less smooth. It's more like a plasma distribution. So then the idea is that we basically take these pictures and we match them with the observations of other galaxies or our own galaxy, and then we see that what the nature of dark matter could be in our universe. Do the observations are compatible? Are they compatible with the fuzzy dark matter model? Are they compatible with the warm dark matter model? Or are they compatible with the cold dark matter model? And with whatever model is able to best reproduce the observation, we basically give credit to that model, that model is the closest to reality. Then the third question that we can ask is, what is the mass and gravitational potential of the galaxy? So this is a very fundamental and a physical question. And that depends on the answer of question 2. But I'll be talking a bit more about this question as well, that what is the mass and the gravitational potential of galaxy. But the point that I'm trying to make through this is that this is the general science strategy, that to test the theoretical predictions, it is absolutely crucial to undertake observational testing. This is not just astronomy, this is not just physics, this is every field of science that you can imagine. If you have a theory, if your theory is not able to reproduce the observations, your theory is basically a good mathematical story. It's nothing more than that. But if your theory is able to reproduce observations, that is when your theory will be regarded. For instance, Einstein, when he gave the general theory of relativity, there were many people even before him who tried to give theories of the cosmos that, okay, this is the law of gravitation, or this is what the space and time look like. But the good point about Einstein's theory was that his theory is able to reproduce the observations of the universe, and that's why we give him that credit, or that's why we say that he's a genius. So this is an important point, that because observation is the reality, your theory is not the reality. Your theory is trying to reproduce the reality. Right, so now I'm again shifting gears, and now we'll be taking Milky Way as a reference galaxy. And let's say that the question that we are interested in is to understand what is the gravitational potential of our galaxy, or what is the mass of our galaxy. It's a decent question, it's a simple question, it's a fundamental question. And the reason for taking Milky Way as a reference galaxy is, of course, because anything that's closer to us, so the stars in the Milky Way are much more easier to observe than the stars in outer galaxy, because it's really hard to observe very further out systems compared to the nearby systems, right? That's just logic. So so we always have most amount of information, most amount of astronomical information for the stars in our own Milky Way compared to the stars in other galaxies, for instance. So yes, so our question is now to understand what is the gravitational potential and mass of our galaxy. And we can't develop a theory for this. We have to rely on observations. We need to get the positions and the velocities of stars to basically try and constrain the potential or mass of our galaxy. So the data for this comes from the satellites and surveys from the astronomical satellites. For example, the Gaia satellite that I showed, and other JWST will give some of the information in future. So from this, we get the 6D phase space information of stars. But what we get is only the present day snapshot. What we get for the stars is only their present day positions and their present day velocities. And I'll try to explain why I'm emphasizing on this point. So I know that this is a new problem of what is the gravitational potential or mass of our galaxy, but I think a familiar problem to you would be, what is the gravitational potential of the sun, or what is the mass of the sun? Because I'm sure all of you are much more familiar with the planetary science rather than the galactic science. But if you imagine, it's really the same physical problem. It's just a difference in the scale of the problem, that here you are using stars to measure the mass and gravitational potential of the galaxy. Here you use planets to measure of AIST. Hello, am I still audible?
Yes, Karthi. Yes, yes,
Okay,
yes.
perfect. So here it's only a difference in the scale of the problem. Here we are using stars to measure the potential and mass of the galaxy. Here we are using planets to measure the mass and the potential of the sun. But it's the same physical problem, that what is the gravitational potential of the stuff that sits at the center. Now, and we have solved, I hope that all of you realize that we have solved the gravitational potential problem for the solar system, the sun. We know the sun, know how the planets are orbiting around the sun, and so on. The reason that, and this is coming from the Kepler's law of planets and the Newton's law of F equals g m over r square and all of that. But the reason that we were able to achieve it, because for planets, we have their 6D information, that is their 3D positions and their 3D velocities of planets as a function of time. We have that complete knowledge. And this is because for a planet to go around the sun, it typically takes a year. For Mercury, it's a bit less. For Pluto or for Uranus, it's a bit more, but it's still of the order of a year. So we can actually observe the full orbit of a planet around the sun. We can measure the position and velocity at each single point. And this is what our great grandfathers have done. This is what Galileo did. This is what Copernicus did. This is what Newton did. This is what Tycho Brahe did, that they actually measured these position and velocity. And after that, they give you those three Kepler's law that we now study, or after that, Newton could give that law that F equals gmm over r square, because those laws were motivated by the observation of the complete orbit of the planet around the sun. But for galaxy, it's complicated. It is practically impossible to measure the entire orbit of a star around the sun. We cannot make that measurement, because if you remember from my second slide, it takes 250 million years for a star to complete its orbit around the sun. And our lifespan is 80 years or 70 years, maybe 100 years if you're lucky. So we cannot wait for 250 million years to observe a star and then start to do our galactic dynamics study. We can't do that. So therefore, all we have is the present day phase space information of stars that at a given, and really, I mean, like a planet, it appears to be moving on the sky. The stars are so distant out into the sky that they practically don't appear to move at all, although they have a speed of 720,000 or 7.2 lakh kilometers per hour. They hardly change their position because they're so further out into the sky. So therefore, all the information that we have is the present day 16 information of stars. It's only the present day snapshot. So now I'll go back to the slide. I hope this point is clear, because this is the main point that we generally miss. And because we are limited by this phase space information, that we only have a present day snapshot and not the knowledge of the complete orbit of the star around the galaxy, we have to make a lots of assumptions about a galaxy. So the kind of assumptions that we make to solve this problem of gravitational potential of the galaxy is that we assume that let's assume that the Milky Way is in a steady state. That is, its gravitational potential is time independent. We have no reason to assume this. In fact, it's a wrong assumption, but we still assume it because that's the only way that we can at least try to get a first approximation answer to this really complex problem. Then we assume that the Milky Way is bound. This is again as an assumption, although a reasonable assumption, but okay. We are assuming that, okay, all the stars tomorrow are not going to fly out of the Milky Way, and in which case the Milky Way will not exist. We are assuming that, okay, all the stars are bound within their own gravitational field and in the field of the dark matter potential. We also assume that the Milky Way is long-lived and that it's dynamically relaxed. All the stars have not assembled only yesterday to form the Milky Way. They have been going around for a long time, and now they're dynamically relaxed. And then we make certain mathematical symmetrical assumptions. You can assume that the Milky Way is spherically symmetric, or you can assume that the Milky Way is axis symmetric, and then you can do all your mathematical physics formulas that you may have learned in your BSc. But we know that if change, then what you do is that you can assume different potential models. You can integrate orbits of stars. You can produce you can produce in simulations your positions and velocities of your stars in your simulation and then compare with the data. So this is what I'm showing you here for a single star. So for example, if you assume potential of the Milky Way is also Keplerian like it is of the sun, which is wrong, but it's a model, so let's assume. So we'll see that most of the stars have elliptical or circular orbits, except for planets around the sun. So perhaps the stars are also moving in the same orbit. If you change your potential and you say that, okay, my potential is not Keplerian, but it's an exponential disk. So this is a much more reasonable assumption because we know that Milky Way has a disk. So then the density of that system goes something like this. And then so you see that the orbit that's shown in blue of the star changes. It's no more a circular, it's going round in kind of a rosette form. If you change this potential from an exponential disk to a ring, so you're seeing this ring distribution of mass here, and then you launch a star, the orbit of the star is again circular. If you change your potential from ring to a rotating bar, so let's assume you have a bar at the center. Milky Way really has a galactic bar. It's a distribution of stars in the form of a bar. And then that bar is rotating, so it's like a churner sitting at the center of the galaxy. Then the orbit of star is rather chaotic, as you can see here that multiple, it's just churning the galaxy. The ultimate idea is to do this exercise for not just one star, but for millions of stars in your computer, and then compare that with your observations that you get from surveys and satellites. And then see which model, this model, this model, this model, or this model is able to best reproduce your observation. An alternate way to solve this problem is to use stellar streams of our galaxy. So here is a simulation from my computer. This is a star cluster that you're seeing here. So this small blob that you're seeing here has about 1 lakh of stars, and it's going around into the potential of the galaxy, and it's getting tidally stripped. So stars, because this is interacting with the gravitational field of the galaxy, so it's getting disrupted, it's getting stretched, and the stars are escaping this star cluster as you're seeing. And then this entire system that you're seeing here looks like an orbit arc that you get in gravitational potential of the system. And then you can basically use the knowledge of these orbit arcs to constrain the potential of the Milky Way. So here I'm showing you detection of some of the stellar streams. So this was basically a simulation that I showed you. These are real observations that me and my team in France, we have detected using the Gaia satellite. So each structure that you're seeing here, so each point here is a star. And these entire structure, this is one stellar stream, this is another stellar stream that you're doing. And now we have taken on this long-term project of using these streams to measure the mass of the Milky Way and to measure the gravitational potential of the entire Milky Way is a project that I'm part of. But the ultimate aim in any scientific study, as I've said, is that you have predictions from the model. Now I'm moving towards the end of the presentation. You have model and you have parameters of model on the x-axis, and your models make different predictions, and different predictions have different probability or likelihood or goodness of the model. So how you test the goodness of a model is that which model parameter or which model is best able to reproduce your data. So for example, in this cartoon figure, I'm showing you that, okay, this particular model at this particular parameter value basically has the highest goodness value when it best matches with the data. So you basically take that parameter set and say that, okay, this model best matches the data, which means that this model is closest to the reality that we get. And that's how we basically solve any modern scientific problem, be it any field, be it even the field of environment, climate change, science, chemistry, biology. This is a typical strategy. Now I'm moving towards the last topic of this presentation, which is talking a bit about the satellites and surveys of the Milky Way, what we get from these surveys or what we aim to get from these surveys. So for the Milky Way stars, what astronomers are typically interested in is to measure their positions, their distances, their kinematics, their velocities, their speeds, also their ages. Is a star 200 million years old? Was a star formed yesterday? Was a star formed 10 billion years? We don't know. The only way to know is through spectra. I'll talk about it. We are also interested to know the chemical composition of stars. We learned from high school days that star is a ball of hydrogen gas, but it's much more than hydrogen. There's helium, there's iron, there's carbon, there's all sorts of elements, and we are interested to know about those elements that a star has, because that gives us idea about how the stars form. It's again an unknown problem. So the European Space Agency has this satellite called Gaia Survey that's currently orbiting around the Earth. And what Gaia satellite is doing is that it's measuring the 6D phase space information of stars. So it's measuring 3D positions and 3D velocities of stars, and it's giving ages and chemical composition for a tiny fraction of those stars. So I've already shown you this picture. This is the actual observation, but this is an artistic impression that how a galaxy may look like if you would view it from the top. And I've talked about the bulge and the bar. This is where the bulge, the galactic center is, the bulge of the Milky Way. All of this is disk. This brown stuff is dust made up of carbon, oxygen, helium, and all of that. These are the two nearby galaxies, small galaxies, the small Magellanic Cloud, the large Magellanic Cloud. Much interest in the community. The community is invested greatly to study these systems, to look for black holes in these systems, to look for stars in this system, to look for dark matter in these systems. And here is a movie from the European Space Agency where it's showing you the motion of stars. And perhaps you can, I'm not sure how the quality of the video is, but you can see tiny motions. So each white point that you're seeing here is a star and it's moving. This, ladies and gentlemen, was a big achievement that was achieved in 2018, because it was practically impossible and we had never ever observed motion of such a large population of stars in the heavens before 2018, when the Gaia satellite produced this data. So this is one of the great achievements of European Space Agency. And now once we have the kinematics of these stars, we can really learn more about dark matter, about the formation of the Milky Way, about the structure of the Milky Way. The second kind of data sets that we have are the spectroscopic surveys. So there are various telescopes on Earth that are observing spectra of stars. And the reason for observing spectra is because spectra also provide velocities. I'm sure everyone is familiar with the Doppler shift or Doppler spectra and so on. So once you have a spectra, the shift from the rest frame, basically, gives you an idea of the velocity of the star. But the spectra also gives you chemical composition, because they are absorption spectra and emission spectra. So that also gives us information about how much iron is there in the star, or how much carbon is there in the star. And so here I'm showing you the two telescopes. The left one is the Sloan Digital Sky Survey telescope. Perhaps you've heard of it. It's taking spectra of the stars. On the right, you have the Chinese Lamos telescope that is also taking spectra of the stars. And there are tens of other ongoing and upcoming surveys of the Milky Way, all of them broadly aiming to understand how our galaxy formed, how do stars form, and what is the nature of this mysterious dark matter particle that physicists talk about. And really, the next, my strong impression is that the next person who will answer this dark matter question will get the Nobel Prize. So this is again to motivate you that if you aim to enter this field, this is to excite you that it could be one of the good questions that you may want to work on. So this is my last slide now, and I'll just quickly go through it. So one of my aims of this presentation was to introduce this young and exciting field of galaxy dynamics, structure, and formation, which broadly tries to address questions on stars, on galaxies, and dark matter. In this field, there's lots and lots of cool science being done. Lots of simulations being run, lots of data being taken. There's lots of funding also available. That is generally a challenge for the fields of science, also for astronomy. But there's lots of people who are funding, lots of universities and governments are making available lots of money and funding. And there are lots of researchers also invested in this field, be it MSc students, PhDs, or seniors. There are some relevant institutes in India that you may consider if you go down that field. There's Department of Physics and Astrophysics in North Campus, where Amit sir and we did our MSc, for instance. There are a few people involved there, if you feel like talking to them. I know some people from IUCA Pune also involved in this field. I'm not particularly sure if there are other institutes in India who are also involved in this subfield of astronomy. But this field is mostly prevalent in in nations of Europe, also in UK and US and Australia. So you please feel free to learn more about this field through YouTube, Google, or other search engines. And I thank you very much for your attention and wish you all the best for future. Thank you.
Thank you, sir, for sharing such valuable and knowledgeable information regarding how do galaxies like the Milky Way form in our universe. The audience must be happy to get the extraordinary astrophysics behind it and are surely feeling joyous to be a part of this informative webinar. May I now request, sir, to answer the queries given by the students in the chat box?
Yes. I only have, see, one question for now, which is please send the link of certificate again. Okay, now I have a question from Ritika Krishnan. What exactly are the limitations in the way of getting to understand dark energy to the best of our abilities in the current scenario? So it's mostly to do with the observations, of course. So for example, JWST will be very useful in it. So one of the ways, so again, I'm not an expert on the dark energy field because that's to do more with the cosmology than with the astronomy. But yes, this much I know that it's to do with the observations, and that's one of the reasons JWST was launched. Because dark energy is to do with the expansion of the universe, and the expansion of the universe is something that happened very long ago in time. And that's exactly what JWST will also do, although it has also been done at some level by Planck satellite, that it will try to get the estimate of how vast the universe is and how fast the cosmic expansion is, because that's where one of the very strong and fundamental constraints on dark energy come from. So the limitation, I'll say that we have hundreds or thousands of models of the universe. I only talked about one model, but if you speak with physicists, each physicist has its own pet model that they're trying to push, but it's to do with the observations. What do you think about dark ages? I only know the definition of dark age. That was an age when, to my understanding, is again dark energy. It has a high uncertainty. That when that dark age formed, these are scenarios that are much talked about again on Google and Wikipedia, and it's an interesting term also, dark age. But it's an age that where no star or galaxy formation took place. So I'm not sure about what do you think about dark ages question mean, but it's just that era when there was no star or galaxy formation, so it was termed as dark age. Sir, how are computer simulations made exactly? It's a good question. It's, if you are familiar, yes. So first I would like to highlight that if you go down the path of research, getting equipped with computer programming is one of the amazing times 10 to the 10 advantages that you will have to learn. Do not run away from it. This is one of the mistakes I made, that I always thought that, okay, theory is most important and computer is not so important, so let me learn theory. But at some point, we are dealing with such advanced problems that at some point, even theoretical physicists these days, they do have to rely on programming languages like C++, Python, or other Fortran or other languages to try and reproduce this, because you can't solve the problem of universe on your paper. So do learn programming languages. And as far as the question is how computer simulations are made exactly, basically you program them up. You have 1,000 or 10,000 of particles, and you program them up in C++ or Python or your choice of language. And then it's basically modeling equation of motion of those 10,000 or 1 million particles. You're basically tracking the motion of those particles. So it's not, so once you get into this problem of learning computer programming, you do it for one particle, that's simple. You do it for two particles, it's simpler. And then you basically run a for loop over 1 million particles. It's kind of that. So it's not that difficult as you would hope, or rather you think. It's really easy once you get into the problem. What part do AGNs or supermassive black holes play in the structural formation and evolution of massive galaxies? So supermassive black holes are thought to be seeds of the galaxies by some people. That initially they were, because black holes, as you know, that they're really dense. They're really massive, they're really dense, so they have this power of attracting everything towards them. So initially in the universe, when these black holes would have formed, the most massive ones, the most supermassive black holes one, the one that sits at the center of our galaxy also, must have attracted the gas and other stars, and around which the galaxies start to took shape. So that's one of the scenarios that also explains the structure and formation of the galaxies, after which the accretion of smaller galaxies took place. Sir, in India, there is no way to pursuing career in cosmology, particularly in this subject. That is wrong. You have lots of opportunities in India of pursuing career in cosmology, astronomy, in anything. But you should also try to think about it a bit maturely, that what you want to do. Cosmology is one field, but when you do research, you do not do research on a broad topic. You do research on a very specific topic. So just to give you an idea, I've talked about so much stuff with you today. But do you remember that one slide where I showed you two of my colleagues from France and I showed you stellar streams? That was really my topic on which I researched. All of the other things that I spoke about is coming from understanding from different people. So it's really up to you that what field of cosmology excites you. I know in India, black holes or radio astronomy, dark matter, black hole or radio astronomy is something people talk about because it's also exciting, but it's not the only field in astronomy. And one of the reasons it's really much talked about in India is because India itself is greatly invested on the topics of black holes and radio astronomy, because we have the telescopes which do those studies. We have the faculty in universities and colleges who do that study. We don't have much of faculty who do galaxies, for instance. We do have faculty in India who does galaxy science also, but there's more of black hole people. Tomorrow, if we have more of galaxy science people in India, then students in colleges will be talking about galaxies. But because black hole is something that people have been working on for about 100 years, it's much more famous field than the field of galaxy that people have only started to work on in last 10, 20, 30 years. But then the advantage of the galaxy field is that there's so much more to be explored now, because in 100 years, most of black hole has been explored. But in galaxy, there's so much more to be explored that is what makes it really exciting, and you can do lots of stuff. Also, sir, and how do we know dark matter exists? What was the purpose to think that there is dark matter, and why do scientists hypothesize the existence of dark matter? Good question. It's hard to explain without a figure, but the idea was that for maybe I can. It's a really good and fundamental question, so I'll try to take help from Google. I'm searching for an image right now. Velocity curve of galaxies. Okay. So now I'll share an image with you. Please wait. Right. Can you see this figure that I'm showing you?
Yes, yes, sure.
Right. So here is the distance of. So this is a velocity curve of the galaxy. So on the y-axis, you have the velocity of the stars, and on the x-axis, you have the distance of the stars from the center of the galaxy. I think this is a better picture. Right. So this explains it. So on the x-axis, you have the distances of the stars. On the y-axis, you have the velocity of the star. So this is the velocity curve that you would expect only from the visible matter of the galaxy. So only from, if you would have only observed the gas and the star, and you use their masses to get the velocity curve. This is the kind of velocity curve. Let me remind you that you've already studied for planets. The 1/r² velocity curve is something that you've already studied for planets. It's the same, again, at a different scale of galaxy. So this is the velocity curve that you would expect if your galaxy only had the stuff that you were seeing, only stars and gases. And this is again 1/√r law. However, to our surprise, the velocity curve that we actually observe is this. This is our actual observation. And this is basically telling us that there's lots of mass that is missing, because higher the mass that your system has, larger the velocity curve will be. Your v is proportional to m at a fixed r. So because there's discrepancy in the expected velocity curve and in the velocity curve that you get from the observation, this discrepancy that why your velocity is actually larger can only be explained by hypothesizing that there is some matter that you cannot see. Otherwise, that would have been in your model. So that's one of the ways. That's one of the observational ways that we have thought that dark matter must exist. That is invisible matter. So yes, there are lots of questions that I'm seeing. That's one of the reasons that I also gave you my Facebook profile. I generally interact with people on Facebook as well. So through my slide, you can find that there's a question: does dark matter interact with itself? It depends on your model. If you allow your model to interact with dark matter, it interacts. If you allow your model to not interact, it does not interact. It's a question that no one really knows, but it's a good question. So yes, so I'll stop answering questions. Thank you for all your polite questions and for your genuine interest in this topic. I'm really glad that you got a bit enthusiastic about this field. And I'm happy to take further questions on Facebook or other alternative platforms.
Thank you so much, sir, for sharing all our doubts regarding the topic so patiently. I am sure this must have inspired many of the budding physicists present in this webinar and resolved their queries by your prior knowledge and expertise in this area.
The Department of Physics of Shahid Rajguru College of Applied Sciences for Women extends hearty gratitude to our honorable speaker, Dr. Khyati Malhan, for conveying a graceful session on fundamentals and applications of physics on 15 January 2022 and illuminating us with the major highlights and sharing valuable insights with us.
Sir, your contribution to the event was immensely valuable. We are grateful for the learning experience that you have provided. Thank you for your vital time from your busy schedule to grace this meeting.
Thank you so much.
Thank you, sir. This marks the end of the webinar on fundamentals and applications of physics. I would like to thank the speaker for enlightening us with his views and taking time from his busy schedule to share his knowledge and experience with us. I would also like to express gratitude to all the participants of the webinar for their presence and contribution in making this webinar a great success. A special thanks to Professor Payal Maghu Ma'am, Principal of Shahid Rajguru College of Applied Sciences for Women, for providing immense support in making this webinar successful. I extend my heartfelt gratitude to the Department of Physics for organizing an informative webinar even amidst the pandemic. At last, I must thank the organizing team and volunteers for making this enlightening event successful.
Okay, thank you, Khyati.
Thank you so much, Dr. Khyati, for taking out your valuable time to be with us. We all have benefited a lot from your talk today and for showing such wonderful slides also. Thank you.
Thank you so much. Thank you so much. It was a pleasure. I was really glad to see so many people making it here even on the weekend, on Saturday. So it's really exciting to see that lots of people are interested to learn so much about, lots of young students and students are interested to learn so much about astronomy. So that was a really good and exciting experience for me also.
Okay, sir, if you don't mind, could you share your Facebook page once again in the chat box so that more students can connect with you and ask their queries over there?
Most certainly, but I mean, my name is so unique, and as you can perhaps imagine that Khyati, it happens to be a girl's name in India, that you'll only see one male profile on Facebook if you type Khyati. But here it is anyway in the chat.
Yeah, thank you, sir. Nice. Okay, sir. Thank you for joining. Okay, thank you very much, sir. Okay.
Bye. Have a nice weekend, everyone. Bye bye. Nice chatting to you.
Okay. Bye, sir.